Thank you.
Thank you. And with this, I'm handing the moderation over to Stu. Stu, here you go. Thank you very much.
Thank you. All right, everybody, with that, we are 3 minutes into the next session, so we'll just roll on ahead, no break. This will be a 60-minute session, and Itamar Holder is our presenter, so I'll turn it over to you. Go ahead.
Hello, everyone. Can you hear me just right?
Yeah.
Okay, that's great. Share my screen. Can you all see it properly? Okay, that's great. So hello, everyone. Itamar Holder, and I'm working for Red Hat as a software engineer. And in this lecture, I'll talk about live migration policies and live migrations in general. I'll have a general recap so that everyone can understand why we need this and what's the motivation for it. So let's go. So this is the general agenda. I'll be talking about what are live migrations, why do we need them, why are they important, how do they work in general, and the challenges behind live migrations. How do we solve the challenges by certain configurations that we have in Kubevirt. Then I'll talk about the problems with the current way of configuring and tuning those migrations. And finally, I'll get into the solution, which is live migration policies. I'll be talking about policy hierarchies and deterministic matching, and the current state and the future state of live migration policies. After all of that, we'll get to a short demo and then to the Q&A. Right, so let's begin. So first of all, what are live migrations? So basically, the migration part is moving a running VM from one node to another, or in other words, from one physical machine into another. The live part of it stands for the fact that we're doing so without stopping the running workload, which means almost zero downtime. Now, we're not supporting cold migrations in Kubevirt at all, which are non-live migrations. Basically, with non-live migrations, there are a lot easier to implement because basically we're just stopping the workload, then performing the migration, and then continuing the workload. This might be a problem in a distributed environment with many moving parts that are all dependent on one another. So we need something better, which is almost zero downtime, and that's why all of our migrations are live migrations. So basically, with live migrations, there are two things that are happening simultaneously. The first one is that we're transferring memory, storage, connectivity, and everything that needs to be transferred from the source physical machine to the target virtual machine. But at the same time, the workload keeps running. Therefore, it's changing the memory and storage and all of that. Okay, so why are migrations so important to us? So basically, in regular Kubernetes environment, we're using containers, not VMs. And containers are designed to have several characteristics. First of all, they're small, they're ephemeral, which means that their state is very, very small. And basically, they're meant to be moved around easily, which also means they have very fast initialization time. So these are all container characteristics, and that every container, generally speaking, should have. Now, one of Kubert's most important design principles is to be Kubernetes native. In other words, our goal is to have VMs and containers living seamlessly together on the same platform, which means that basically VMs need to behave like containers in the same way. So, but this is not easy because VMs are very different from containers. They are harder to move around. They do have significant state. These states can be open files or the state of the kernel, or the state of the VM's hardware, and among other stuff. So basically, it has a huge state comparing to a container, and it's not ephemeral. And lastly, they're large, which means that their boot time is much bigger. Initialization time of containers, generally speaking, is a matter of seconds. And with VMs, it can easily become a matter of minutes. So this can bring many challenges. But when are we actually moving those VMs or containers around? So one example for that is while draining a node. So draining a node is basically moving around all the workload outside of the node, so we can turn it off, update it, or whatever, and basically disconnect it temporarily from the cluster. So when we're speaking about containers, basically all of the containers are being moved out of the drain node, and that basically means that we're deleting all of them and starting new instances in other places, which is a pretty easy task with containers. So this is how it looks like. Let's say you have node 1 and node 2. So basically, we're deleting all of the containers in the first node and recreating them in a second node. Of course, in reality, it generally happens gradually. We can delete one container and then create an instance elsewhere, and then delete another instance and make another instance elsewhere. But eventually, this is what's happening. We're deleting the instances and basically simply creating them in another machine. For the reasons we mentioned before, this can be done naively with VMs. We can't just delete a VM and start it elsewhere. It will take minutes to boot. It will lack the state of the previous instance, and so on. Another example is upgrades. So this is done basically in the same way. If in Kubernetes with regular containers we want to upgrade deployment, for example, then basically we are deleting an instance and recreating an instance with a higher version until all of the containers are removed and new containers are created. And for the exact same reasons, this is a problem with VMs. So more examples exist, like load balancing and so on, but it's very reasonable to assume that more of these will pop up in the future, because basically that's how containers are by design. Again, they are designed to be moved around easily. So a lot of future stuff in Kubernetes might use these characteristics, which are not going to be which are going to stay with containers. So to speak about migrations, I'll present a few kinds of migrations, and we'll see what are they good for and how to use them. So basically, first of all, I'll show the 3 steps which are common to every migration that we're going to have. So first of all, the first step is to basically create another VM instance at the target node, which is pretty similar to the first step we're doing with containers. Simply create them elsewhere. The second part, which is very different from regular containers, is that we have to move the state around from the first VM to the other one. So in Kubevirt, we basically establish a communication between 2 of those VM instances, and the state is being transferred from the source VM to the target VM. And finally, again, like containers, we simply remove the source VM and let the target VM run. So this brings up a few challenges. So the fundamental challenge with migrations is that basically the memory keeps changing. Eventually, the target needs to receive the up-to-date memory, and only then we can stop the source VM and start running on the target VM, which is called a migration handoff in Kubevirt. So one of the concerns is that this whole process will never converge, and this can be caused by frequent writes to the memory. But first, let's be optimistic and show the happy path. So this is a pre-copy migration. This is the default migration, and basically, if nothing wrong happens, so this migration should be converted successfully. So what we're doing here is basically we're creating the target VM instance on the target node, and we're running on the source VM. And now what's happening is that we're transferring all of the state to the target node. When the state is transferred completely, and so we start running on the target VM and delete the source VM. And this is all great, but again, with frequent writes, migrations can be stuck. And the main problem is that while we transfer a memory block from the source to the target, it can be mutated at the time we're transferring it. This means we have to copy the block again. And the scenario can occur over and over, causing migrations to hang, which is basically a problem. So this is the illustration of it. So basically, if VM1 frequently writes to the same memory block, we'll be moving it again and again and again. If the writes are frequent enough, this will never end. So one of the solutions we have to that is called Auto-converge. And this is basically a technique for overcoming the scenario I explained before. The idea is pretty simple. Basically, we throttle the source VM CPU in a logarithmic pace. And this means that at the beginning, the CPU will use all of the VM will use all of the CPU. And we will gradually throttle the CPU to help the migration converge. So basically, first of all, and just like pre-copy migration, the source VM is the one that is running at the beginning. So the source VM starts running with 100% CPU, and over time we decrease the CPU or throttle it to the point that it can converge and all of the memory state is being transferred into the target. And then we are running on the target, we can remove the source VM, and the migration is done. So it has pros and cons. So the pros is that basically convergence is guaranteed eventually. If we throttle the CPU enough, we guarantee that the writes aren't that frequent. And that means that basically eventually the migration will end. It will never hang forever. Another pro is that it's completely safe. We don't risk anything. And another pro is that if the migration is fast enough, we don't throttle the CPU, and the migration is basically acting as a regular pre-copy migration. The cons is that basically we slow down the workload. It might be a problem for certain workloads. And if we're taking this approach to the extreme, we get to a point where we completely throttle the CPU, which means this is not really a live migration by all aspects, because again, in the extreme, we are almost stopping the workload, migrating it, and then starting it again. So we have another way to deal with this, which is a post-copy migration. And a post-copy migration basically means that we're as we create the target VM, we're start running on it right away. The idea is that if the VM tries to access a page it does not own, which is basically a page fault, it asks for the source VM to transfer it explicitly. If the target VM does not ask for pages explicitly, which means that it runs on the memory blocks it already have, then other pages are being transferred in the background until all the memory is transferred. So let's look at on how it's done. So basically, we create another instance at the target node, and this instance starts running immediately. Once the target VM tries to access a memory it does not own, there is a page fault. It asks for the source VM for the specific page that it's lacking, and this page is being transferred. Afterwards, when it continues running, basically other pages are being transferred in the background, and finally the migration is done. So the pros here is that, again, every page is transferred only once, because unlike pre-copy migrations, what's happening is that if the page is being mutated, we don't care. We don't have to transfer it again, because it's being mutated at the VM that is actually running the workload now. Another advantage is that the migration almost never hangs, and we are using less network bandwidth. But we have serious cons here. The first one is that it's pretty dangerous to do so. That's because we don't have any VM instance that has the full desired state. So, for example, what happens if one node crashes? We can't recover the VM because every VM instance holds only a partial state of the VM. Another con is a slow warm-up. At first, basically, when the target VM just starts running, we will most certainly hit a page fault because we don't have any memory. So at the beginning, there will be a lot of page faults, which basically is a blocking operation. We will stop the workload because it cannot continue, and it will wait for the block to be transferred. And another con is that, in general, in the average use case, it's a slower mode, slower migration mode. So basically, I showed just one kind of migration configuration, but we have many others, like the maximum of parallel migrations per node, and the maximum migration bandwidth, and dedicated migration network. And of course, we will have more configurations in the future. And basically, there is no best configuration for all use cases. So to sum up everything I've just said, so with 3 rules of thumb that are not really 100% accurate, but if the VM is running, is not performing frequent writes to the memory, we might prefer using pre-copy migration, which is the safest and fastest in the average use case. If we are having frequent writes to the memory and we're okay to risk the workload, post-copy sounds great. If we don't want to risk anything, but we're okay with slowing down the workload a bit, maybe auto-converge is good. But the main point I'm trying to make here is that tuning migrations configs is not an easy task. There are many considerations, and it varies significantly between environments. So in order to tune these configurations properly, one needs to understand the priorities of the VMs that are running in the clusters, what the VMs are doing, what are the exact workloads that are occurring inside these VMs, and what is the environment? Is the network strong? Is the network fast? So basically, to tune all of these, you pretty much have to be an expert. You have to understand the environment. You have to understand the different configurations, and not everyone can do so. So what do we have today? And by today, I mean before log migration policy. So Kubevirt allows to tune migration configs, but only cluster-wide through Kubevirt CR. So basically, Kubevirt CR, for the ones that don't know, is the place when you can have the specifications cluster-wide for Kubevirt. So this means that you cannot specify different configurations for different VMs. And this is very problematic because the configurations, as we just saw, are very tied up to the workload that's running inside of the VM. So we need something better. So what do we need? What do we want to have? So on the other hand, we don't want VM creations or VM migrations to be very complicated. So we don't want somebody to consider all of this in order to create a VM or to migrate a VM. And it would be best if somebody, some expert, the system admin or somebody, will basically tune the right configurations. And when someone creates a VM and tries to migrate it, what will happen is that magically the best configuration will be matched to the VM migration. To me specifically, it reminds a bit of security policies like SE Linux. So, for example, if I open up my Fedora and start editing files or creating folders or whatever, I am bound up to certain security policies. I'm not aware of them. I don't care about them, but I am matched to some security policy that somebody that is more expert than me on the matter defined beforehand. So we basically we wanted to have the same here. Somebody to create them all, and then when somebody else creates the VM, tries to migrate it, the right policy would be matched magically. So these are live migration policies. These policies are matched to migrations on the fly. So the admin will have to define migration policies in advance. And then when migration is requested at the time of the migration, it would seek for the most detailed policy, and this policy would match the VM. And I'll be talking more on that in a second. And whoever tries to create the VM or migrate it doesn't have to know about these policies and about all these configurations and all the considerations behind them. And another nice thing that I'll be talking about in a minute also is we can make a hierarchy of policies. So a migration policy is matched to a VM by VMI or namespace labels. And in order to match, the specified labels have to match all of the specified labels. And again, the most detailed policy, which means basically the policy that requires the most labels, has precedence. This allows creating a hierarchy of policies with different priorities, of basically priorities that are more confined or have more precedence. If no policy is matched, then we fall back to the Kubevirt CR config that would be applied. And if a policy defines only some of the configurations, but not all of them, the value of the missing configuration would be also be taken from the Kubevirt CR. So we can picture it kind of this way. So we can have a development namespace, for example, and a production namespace in our cluster. Maybe we want the max bandwidth of the migrations for the development to be 1 gigabit, and we want the bandwidth for the production to be unlimited. Maybe under the production, we have backend components and front-end components, which you use dedicated network or not use dedicated network. Inside of them, we could have different apps or microservices that would also be using different configurations. So as you can see, the nice thing about here is the hierarchy. So the VMs, just a VM, a regular VM under production would have unlimited bandwidth, but a VM under production that is also an engine VM would have post copy. So this is kind of neat, and this is how the manifest looks like. We will see the manifest also in the demo, which I'll be showing in a minute. But in general, this is how it looks like. Basically, the spec consists of two parts. The first part is a migration configuration, which can be the bandwidth or allow auto-converge or anything like that. And the second part is the actual matching to the VMs. And as you can see, we can match the VM by namespace labels or by VMI labels. And you will see this again in the demo in a second. As I said, the most detailed policy has the highest precedence. This means that it's possible to have more confined policies for more specific scenarios. And the detail level is simply the number of required labels. And again, they all have to be matched. If one label does not match, the policy is not matched. And namespace and VMI labels have the same weight. They're both considered one detail level. Yeah, so also another thing that it's important to mention is that the matching is always deterministic. So if we have two policies with the same detail level that are matching to a migration, we simply sort the matching migrations by lexicographic order of the name and choose the first one. This is, of course, somewhat of an arbitrary decision, but it does guarantee that the matching mechanism is deterministic. So the current state is that live migration policies are implemented and merged and are part of Kubevirt for the non-release. The API version is still in V1 Alpha 1. And the current configurations are auto-converge, post-copy, and migration bandwidth. In the future, of course, more configurations will be supported. For example, dedicated networks, related knobs may appear, and perhaps new methods to match to VMs. And of course, we will be glad to have more ideas about that from the community. So we're open to new ideas. And now we can start the demo. Okay. So these are all the folders that I prepared, and now we will walk through them and present. And another thing is that this is basically what I'm going to do in the demo. So basically, we're going to define some configurations in Kubevirt CR. We're going to define a production namespace with a policy that's supposed to be matched for the namespace. And then we'll create a VM. And we will expect that that this configuration from the policy will be matched, and all of the other configurations that are not specified in the policy will be matched from the Kubevirt CR. After that, there is another policy that is supposed to match a DB VM, which is basically, again, more detailed than the first policy. We will see that these configurations apply. And again, the ones that are not listed here are applied from the Kubevirt CR. And just a quick word about this configuration, which I didn't mention, is basically the amount of time we have to wait per gigabyte until we're transferring into post-copy migration. Basically, for the demo purposes, we can just accept it as it is. Okay, so let's begin. So first of all, we'll post the production namespace. This is a regular Kubernetes namespace, and as you can see, we have a label that says type production. The name of the namespace is intentionally different to emphasize the fact that the policies aren't being matched to namespaces by names or anything. They're only being matched by labels. Okay, so let's post the namespace. And great, and as you can see, the namespace is created. And now I'm just making an alias, so it will be easier to not include the -n argument all the time. So K, of course, is kubectl, and KP is kubectl with this namespace. So now we have to patch kubevirt again. So we're going to insert these configurations into kubevirt, and let's see how it looks like. Okay, so first of all, we're turning on the live migration feature gate. This is just because we want to use live migrations, and we have to enable the feature gate in order to use them. And finally, this is the migration configuration. So first of all, we're making pre-copy mode as the configuration here. This is being done by simply turning off auto-converge and post-copy. If they're both turned off, then the default one is a pre-copy migration. And also, as I showed in the presentation, we have another two configuration, which is the bandwidth migration, which is 100 gigabytes, and the completion timer per gigabyte, which is 1.5K. And this patch script just patches it to kubevirt, and we're done. Okay. Okay, so now taking a look at the actual policies. So we have, again, a policy for the DB VM and a policy for the production namespace. So let's have a look. So the production policy, basically, as we saw earlier, there are two sections. The first one is the configuration itself, which is that the bandwidth is 20 gigs, just like showed here. And we're matching it only to a namespace by the type reduction, as we saw earlier, that our namespace has. And this is the second policy. In here, we are allowing post-copy. The bandwidth is different, and we're matching it by two labels, which means, again, that it's more detailed. It has precedence. So the type is production for the namespace, and an app label, an appdb label for the VMI selector. Now we will post them both into the cluster. And as we can see, they are both posted and created in the cluster. So now we can move on. So we have two more directories here, one for the VMIs. So we have, again, the DB VMI and the monitoring VMI, which we are going to create now. So nothing too interesting in here. Just a second. So basically, the thing that is important is the label part, right? For the monitoring one, it's not that important because no policy matches to this label. But for the second VM, the DB VM, we have also the app DB, as you saw in the policy. Other than that, there are just regular VMs, nothing too important. And now we can see that I've made two migration jobs. So the role of a migration job is basically to perform a migration. The only interesting part is the spec, which refers to the VMI name. So again, nothing too interesting here, just to show you what's going on. All right, and now we can move to the more interesting part. First, we'll create the monitoring VM. So the VM is created. We'll just wait for it to start running. And as you can see, it's running on node 1. Now we'll try to migrate it. And soon enough, it will be migrated. All right. So as you can see, the VM is now in node 2, not node 1, which means that the migration is done, and we can have a look on what configuration actually applied. So let's take a look on the section here. So basically the migration state shows us all of the different configurations that were used. So as we can see, the auto-convergence, the post copy are both false as we expected from the Kubevirt CR, because we wanted to use post copy, pre-copy, sorry. If we will take a look on the completion time out per gigabyte, we didn't specify it in the policies anywhere. Therefore, we have it here, right? The value is being taken from the Kubevirt CR. The migration bandwidth on the Kubevirt CR is 100 gigabytes, but on the match policy, it is 20 gigabytes. Of course, the policy has precedence, so we can see the 20 gigs here. So everything is expected. And also, you can see the migration policy name that was matched, and you can see that this is the policy production, right? This policy. So great, everything works as expected. Okay. Now we'll delete the VMI just so everything is clearer. And we will create the second VMI, the DB VMI. And again, it's being created. And you can see it's running on node 1. Now we'll migrate it. Oh, just forgot the P there. Right. And soon enough, it's now migrated to node 2. Okay, and again, let's take a look on a VMI. And once again, what we can see here is that basically this policy is says that it wants 30 gigabytes of bandwidth. Again, this one has precedence over everything, over both this policy and the Kubevirt CR. And as we can see, we do have 30 gigs of bandwidth here. The 1.5K for the completion time out per gigabyte still is being taken from the Kubevirt CR. And also, we allowed post copy here. And as we can see, post copy is allowed. Right, so that's it for the demo. And the last part is Q&A, so if somebody has a question.
Hi, Itamar. There were a few questions in chat, but because the chat will not be part of the recording, please allow me to recap real quickly the discussion that's gone on. Andre had asked if it's possible to live migrate a VM when using a GPU. And the general answer there is no, because we cannot copy the memory of the device. It's not possible to do the migration itself. Follow-on question was if the same applied to a vGPU, and Vladek had responded with vGPU is different. In general, it can be migrated, but we don't support this right now because there is no official support for this in QEMU. Some vendors, such as AMD, do support SROV GPU virtualization migration, but we don't have the hardware to even try it at this point. Andre did ask a question in the middle of that, and that was perhaps we should use the MESA drivers instead of the hardware GPU drivers. Then we could get the memory access to do the live migration. And is anybody working in that direction? As far as I know, no. Is that what you think, Itamar? I'm not aware of anybody working towards that.
Can you repeat the question? Sorry, I was trying to read the chat.
Yeah. Sorry. The question was, perhaps if we use the MESA drivers instead of the hardware GPU drivers, then we could get memory access to do the live migration. And is anybody working in that direction?
Actually, I can't answer this question. I'm sorry, but you can always email me and I will try to look it up.
All right, so then we, Prasanth asked a question, can migration policies be used to pick certain VMs over others during node drain?
I'm not sure what you mean by that, because in a drain, we're basically moving all of the VMs out of the node. But maybe the question is which VMs to drain first. But either way, we don't support it right now. But again, this feature is in very early stages, so we'll be happy to have new ideas from the community. So you're more than welcome to participate in this.
There's a request that you stop sharing your screen. And Chris Caligari asked, can't NVIDIA GPUs share memory via InfiniBand?
Again, I can't answer this question, but but you can any questions you can email me and I will respond. I will post my email in the chat.
We'll give it just a minute to see if anybody's still typing or asking a question. We still have 20 minutes until the next presentation is scheduled to start, so plenty of time. As Josh pointed out, if anybody would like to ask a question aloud, we can turn on your microphone and camera and allow you to do that. Okay, it looks like we've got no more takers in terms of questions. So with that, we can go ahead and stop this presentation, and the next one will be scheduled to start at 16:35 UTC.